This is the third part of our notes on electrostatics. We're going to concentrate on combination circuits as well as capacitors. This is a real typical diagram here. We have multiple resistors wired in a combination. When we have stuff wired in combination, the first thing you need to do is go down until you have one resistor and one battery, and then go all the way back up. Now, this is a pain to do. So if we look along this, if I start at my terminal at point A and I continue along, I have go through a resistor, which is fine, that's in series, then I have a junction point. But if I look at that junction point, I have one in here, and then I have multiple resistors through there. So I'm not able to combine those. So if that doesn't work, the next step is to start at the very end, the last junction. And if you can see through this last junction, I'm going to have three resistors that are in series. And so to determine our total resistance in series, we simply add up these three resistors, and if R is 2, then my R total will be 246, 6 ohms. Now, don't be lazy. You have to rewrite this every single blasted time. And so as I rewrite this, I have this, and then I combined all these, so they're going to be in parallel with this last one. So this becomes 6 ohms. This is 2 ohms, and hopefully you can now see that these two are in parallel with one another. There's only one resistor in each parallel part, and so I can combine those. And so when I combine resistors in parallel, I have to do the reciprocal function. So I'll do 1 over 2 plus 1 over 6, and then don't forget to take the inverse of that, and you get 1.5 ohms. A quick way to check. This total resistance needs to be less than any one of these two resistors that are wired in together. And so 1.5 is less than 2, so we're in pretty good shape. So when I combine those, this becomes the 1.5 ohms. That's these two put together. Then, starting back from the end, hopefully you'll see that I will have three that are wired in series. And so to calculate that R total, I'll have 2 plus 1.5 plus 2. And so when I put those together, I will get 5.5. Oops, but that doesn't go there. That's these guys put together, so I'll have to wire that in parallel. And so that is my 5.5. Keep going on. I have two of them that are in parallel. Since they're in parallel, you should be able to see they're the only ones in parallel. So I'll have 1 over 2 plus 1 over 5.5. And so when I do this math, I will get I'll round to make my life easier, 1.5 ohms. Redraw, just about done here. And so this becomes 1.5. This one is 2. This one is 2. One last step here. Put them all together. And when I do so, I'm going to get 4 plus 1.5 is a total of 5.5 ohms. Now, it doesn't say to do so, but we're going to keep going on this. And we're going to assume that it's connected to a 9-volt battery. And then we need to calculate V and I through each one of these. Since we're down to one resistor, I know that my volts have to be 9 volts. I then can calculate I using V equals IR. And so when I do this math, I'm going to get 1.6 amps. As we look around here, I look where that 5.5 came from. It came from these two that are in series. What stays the same in series? Is it V or is it I? You need to have this memorized. Current. I stays the same in series. So I'm going to have I equal to 1.6 amps. I equals 1.6 amps. I then need to calculate the volts going through each one of these. And to calculate that volts, again, all I'm doing is V equals IR. And I can be able to do this math and easily check to see my work. And again, all I'm doing is putting this into my calculator. Is there a way to check? Absolutely. If I add up all of these voltages, 3.2 plus 2.4 plus 3.2, I should get pretty close to 9. In this case, I got 8.8, just because of rounding, that happens. Now notice these two have not changed, and they will not change anymore. And so I am done with them. I can write them all the way up if I wanted to, because I know what those are. What did change are these two blue ones. The two blue ones became this 1.5. Hopefully you can see that these two are in parallel. What stays the same in parallel? My voltage. 2.4 volts here, 2.4 volts here, and now I need to calculate my I. When I do that math, I'm going to do 2.4 divided by my 5.5, which gives me a 0.44 amps here. And, what's the value of this resistor? I didn't write it down. Hopefully you know that's that 2 ohm one. That's before I converted anything. And so I get an I of 1.2 amps. Moving on up. Notice that these are done. I have finished with these. I know what these three are, and so I'm going to cheat and go all the way up here to the top and write these down so I don't have to mess with them anymore. I know this is 1.6 amps. I know this one is 1.6 amps. I know this I is 1.2 amps. And I calculated the V here to be 3.2 volts. V is going to equal to 3.2 volts. This V is going to equal to 2.4 volts. So I'm just going to put an X through all these because I know they're all done. Looking at the yellow ones, the yellow one became this 5.5. This 5.5 came from the three that are in series. What stays the same in series? Current, 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 current. And so I can write my I as 0.44 amps all throughout there. Then I need to calculate my V. How do I calculate V? V equals I times R. So 0.44 times that 2, which I didn't write down. Hopefully you know where that came from. This is going to be 0.88 volts. And then I'm going to multiply my 1.5 times my 0.44 and get 0.66 volts. Keep moving up. Now, am I done with these two R's in the middle? That's a yes. So I can write this V as 0.88 volts. This V is 0.88 volts. I know my I is 0.44 amps. My I here is 0.44 amps. So I'm done with this guy. I'm done with this guy. Where did this 1.5 come from? The two that are in parallel. So my V is going to stay the same. So I'm going to have 0.66 volts going through each path. I then calculate my I by doing some division, and I get 0.11 amp there and 0.33 amps there. Okay, so this one in the middle is done. V is, sorry, color, it's red. My V is 0.66 volts. My I is 0.33 amps. One step from this over here in the end. And so when I calculate that, my I is going to stay the same. So I'm going to have 0.11 amps through each one of these. And to calculate the V, I do V equals I. It's going to be 0.22 volts. This computer's making a really loud noise, which has me worried. Hopefully not picking up this awful loud noise. Okay, so is there a way to check all of this? The answer is yes, there is. What you want to do is you want to pick one path. So let's start here, and let's do this yellow path and check my voltages. So I'm going to have 3.2 plus 2.4 plus 3.2. Is that pretty close to 9? When I do my math, I get 8.8, so that's a pretty good little path. Let's take a different path, and if we take a different path, let's go all the way along the outside, that blue path right there. So if we check our blue path, I'm going to have You probably can't see that. 3.2 plus 0.88 plus 0.22 plus 0.22 plus 0.22 plus 0.88 plus 3.2. And when I add all that up, I get 8.8 again, and so that's close enough. And so I am fairly confident that my math is correct, except for some rounding errors. Again, very complicated, not so complicated as much as tedious. Go down to one resistor, and then all the way back up. Find the current and the potential difference through each resistor in the figure below. Again, this one's a little bit easier since I have two. I'm going to start with these two that are in parallel. I want to combine in parallel, and so I have to know this formula, 1 over 500 plus 1 over 700. And so when I calculate that total resistance, I am going to get 291 ohms. Need to redraw that. So I have 400 here, 291 here. Hopefully you can see these two are in series. And when I combine things in series, I simply have to add them up, and I'll get 691 ohms. Since I'm down to one battery, one resistor, I know my volts have to be 12 volts here. I can then calculate my I using V equals IR. And that current's going to be 0.017 amps. Where did this 6.91 come from? The two that are in series. I stays the same in series. And then I'm going to have to calculate my potential using V equals IR. I'll multiply those two numbers together. 6.8 volts there. And 4.9 volts there, which when I add them up comes pretty close to 12. The 400's done. I know this is 6.8 volts. I know my I is 0.017 amps. Now, where did this 291 come from? The two that are in parallel. What stays the same in parallel is my volts. So this is going to be 4.9 volts. And then I'll have to calculate my I. Oops, let's do that again. 4.9 divided by 500 is going to give me a current of 0.089 amps. And my I here is going to be 0.007 amps. And a quick way to check yourself, we know that this should be 0.017 amps going through this path. So if I add up the current going up and the current going down, it should equal that 0.017, which if I do a check, it does. Alright, continuing on. The next thing we're going to talk about is a capacitor. And when we combine capacitors, they're opposite of what we do with circuits, which isn't so bad because what you're going to do is, again, combine them all the way down to 1, and then you'll go back up. But instead of using V equals IR, we're going to use the capacitor equation, which is QVC. So let's look at this. These two are in parallel. When we have capacitors in parallel, to calculate the total capacitance, all we have to do is add these guys up. And so as we do this, I'm going to redraw this, and notice these capacitors and my batteries are going to look the same. Don't freak out, it's not that difficult to tell the difference. And so I've got 3 here, and then I'll add 4 plus 2, which should give me 6. Again, I've got 5. Now these two are in series. To calculate capacitors in series, we're going to have to do the reciprocal function. So when we do our reciprocal function, just like we did, we'll take 1 over 6 plus 1 over 3, then I have to flip my answer. The capacitance becomes 2. And so when I combine these, I'll get a 2 here. Notice these two are now in parallel, and so when I combine them, I will get 5 plus 2 is 7 microfarads, and that's connected to a 100-volt battery. So my V here is 100. How then do I calculate my charge? Which is Q. God, I'm turning into my own level, kids. Q equals VC. Q is what I'm solving for, so I'll just multiply 100 times 7, and that will give me 700 microcoulombs. We have to then continue all the way back up, and just like before, when we're in parallel, one of these two are going to stay the same. What stays the same in parallel is the volts. So this one will occur with 100 volts. We'll then plug it into QVC to calculate my Q. So that's going to be 500 microcoulombs, 200 microcoulombs. My 5 is now done, so I can just continue on all the way up, writing what I've already solved for. And where then did these two come from? The two that are in series. What stays the same in series is the charge on the plates. And so each one of these will have a 200 millicoulomb charge, or microcoulomb charge actually. And then I will plug again into Q equals VC. And that's going to equal to V times the charge, the capacitance, which is 6. And this is micro and micro, so I can not worry about the signs. And so I'll have 200 divided by 6 gives me 33 volts here. And 200 divided by 3 is going to give me 66.6 volts here. So my 3 is done. 66.6 volts here. My Q will be 200 microcoulombs. And so now I see where this 6 came from. Where did the 6 come from? These two that are in parallel. What stays the same in parallel are my volts. So this will be 33 1/3 volts here, 33 1/3 volts here. We then need to calculate the Q by doing some multiplication, and 133 microcoulombs here, and 66.6 microcoulombs there. So again, when we have capacitors, they're going to be very, very, very similar to resistors. The only thing different is you're going to do the opposite when you're combining capacitors versus resistors. Alright, how we going? Okay. EMF and terminal voltage. A device is a battery that transfers one type of energy into electrical energy. This is called electric motive force, or EMF. If you see EMF, all I want you to think of is a battery, and a battery provides potential difference. That is it. That's all you have to worry about when you see this EMF. But what this is saying is, even though this battery is rated at 1.5 volts, is that what actually comes out when I connect it to a light bulb? Well, in our perfect physics world, that's what comes out. However, in real life, we're going to have something called internal resistance. This is the chemistry messing up. It's how much the chemistry messes up. And so we label that internal resistance R. When we solve for this, it's just like we have another resistor. So if I was drawing this circuit diagram and I'm being connected to this light bulb here, we would indicate this internal resistance. It's really inside of this battery, but we never separate those plates as we're drawing this. And so we'll draw it as simply another outside resistor. And that was known as the internal resistance, and that's that big R of the light bulb. And so this VAB is what actually leaves the battery, is equal to this EMF, which is what it is rated, 1.5 volts in case of a AAA battery, minus my I times R. And that's that value of that internal resistance. We're going to calculate that voltage, V equals IR, of that internal resistor. So again, you're probably going to freak out, but let's look at a problem. It's not that hard. A 9-volt battery whose internal resistance is R equals 0.5 ohms is connected and the circuit is shown. How much current is drawn from the battery, what's the terminal voltage, and what's the current in the 6 ohm resistor. We're going to work this. We treat that internal resistor exactly like we did before. We have to combine those two first because they are in parallel. And so I'm going to redraw all of this. When I combine these, hopefully you see this is 1 over 8 plus 1 over 4. And when I do that math, I am going to get 2.6 connected to this 5 ohm here. So this is 6 and this is 10. That's 5. My internal resistance is 0.5. I'm going to combine the 6 and the 2.6 next. And when I do that, I'll end up with this right here. That's going to be 8.6 ohms here, 10 ohms here, and 5 ohms here. Getting closer now. I'm going to combine the 2 in parallel next. Yeah, my computer's making awful noises. This is not good. And again, I got to take the reciprocal of all this mess. And so I let my handy dandy calculator do my work for me. And I'm going to get 4.6. Now I'm down to easy breezy series circuit. Should be able to add all these together and get 10.1 ohms. And unfortunately, we have to go all the way back up. My voltage on my battery is 9 volts. To calculate my I, V equals IR. And so I do that math and get 0.89 amps. So my I here is 0.89 amps. My I is 0.89 amps. My I is 0.89 amps because current stays the same. Calculate the V through each one of these. 0.45 volts here. 4.1 volts here. And 4.5 volts there. Keep going up, and I'm going to ignore the 0.5 and the 5 because it's done. These two are in parallel. In parallel, the V stands the same. So I'll have my 4.1 volts. Calculate my I using V equals I times R. And yes, I just did that on my calculator like an idiot. And divided by 8.6 gives me a 0.48 amps. Keep going up. The 10's done. Where did these two come from? The ones that are in series. So my I here is going to be 0.48 amps here. I is going to equal to 0.48 amps there. And then I need to calculate my V. 0.48 times 6 gives me a 2.9 volts. 0.48 times 2.6 gives me a 1.3 volts. All the way back up. Where am I now? One more. My V is going to stay the same because I'm in parallel. Hopefully you're getting this because I'm moving through this very quickly. Doing it in my calculator, letting it do my work for me. So I get 0.16 here, and this is going to be 0.32 here. So let me go ahead and write down everything that I have up here at the top. 4.1 volts and let's see, 0.89 amps is down here. And, sorry, 0.89 amps is there. And that 6 is 0.48 amps. The V here is going to equal to 2.9 volts. The V through that 10 ohms is 4.1. And last but not least, the last V's are 0.45 and 0.45. Okay, so let's see what the problem even asks for. How much current is drawn from the battery? Well, the answer to A is down here at the bottom. How much current was actually drawn when we have one resistor? That's going to be 0.89 amps. What is the terminal voltage of the battery? Remember that terminal voltage is what it's rated at, which is 9 volts, minus the voltage of that internal resistor. And so that is I times R, or the V. And so when I do this math, what is actually coming out of that battery is 8.55 volts. In C, what is the current in the 6 ohm resistor? We got that at 0.48 amps. Again, these take practice, and the more you practice them, the faster you become at them. They're just long, tedious, and take lots of paper. EMFs in series and parallel. So EMF, remember, if you see EMF, all you need to think of is a battery. So when two or more EMF sources are arranged in series, the total voltage is the algebraic sum of their receptive voltage. Now, this is if they are wired positive, negative, positive, negative. You have to put them in the correct order. Positive, negative, positive, negative. So what's the total EMF in this battery? I'm going to add this up and get 3 volts. Now notice this one's wired screwed uppy. Negative, positive, positive, negative. These aren't going to help each other. They're going to suck away from each other. And so when I combine 20 and 12, I get 8 volts. In figure B, this is the way an alternator and a battery work. The alternator is 20 EMF, charging back, and so forth. Okay. Voltage of EMFs range in parallel will not increase the voltage, rather it provides more energy when large currents are needed. An RC circuit is one that contains both a resistor as well as a capacitor. Notice resistor, 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 and then I throw a capacitor on there. The purpose of the capacitor is to store electric potential energy. The capacitor can act as the potential difference source, i.e. a battery, for a short period of time if we disconnect that battery. The purpose of a battery is to provide the charges on the plates. Once fully charged, the capacitor will have a full potential difference. For example, below, once the capacitor is fully charged, because these are wired in parallel, whatever voltage this guy has is how much voltage is going to be stored in this capacitor. And so to help you understand that, we will work this problem right here. It's all connected. Then what's going to happen? Okay, so if we ignore this, if we just look at this path right here, I'm going to have to do some dreaded math. And so this is 6 and 4. These two are in series. And so when I combine them, I will get 12. Combine the two that are in parallel. And when I combine the two that are in parallel, I will get 3 ohms there. One last shot, I'll get 9 volts connected, sorry, not 9 volts, 9 ohms, because 6 plus 3 is 9, connected to a 72 volt battery. Made it pretty easy on us in terms of doing math in our head. And so we're going to get 8 amps here. Current stays the same. I equals 8 amps. I then need to calculate my V. Doing V equals IR. 48 here. 24 here. Keep going up. The 6 is done. I don't have to worry about it. I can write it on. 8 amps. My V is 48 volts. The 3 came from the two that are in parallel. So in parallel, my voltage is going to stay constant. So that's 24 volts here. 24 volts here. To calculate my I, we'll do 24 divided by 4, which gives me 6 amps. And 24 divided by 2 gives me 2 amps. And so now our 4 is done. And so I know this is 6 amps, and I know this volts are 24 volts. Now, where did this 12 come from? The two that are in series. And so this voltage is going to be 24 volts. No, it's not, because it's wired in series. What stays the same in series? Current. And 4 volts, 20 volts. Let's check some math. Let's go along this outside path. 48 plus 4 is 52. Plus another 20 is 72. I'm done. I did it correctly. So let me get rid of these highlighted values. So now, what's going to happen is this thing's going to become fully charged. We're going to close this up. Once we close this up, the voltage here is going to be split between these two things. Because they're in parallel, they will eventually get the same voltage when this thing is completely charged. Because this path has 20 volts, this path will end up with 20 volts. And so now I can just use Q equals VC. 20 times 3 will give me 60 microcoulombs. Calculate the energy stored in that capacitor. You got to remember that formula. 1/2 CV. No, 1/2 QV. 1/2 QV. So 1/2 times 20 times 10 to the minus 6 times another 20. So that's going to give me 10, which is 600 microjoules, because energy is in joules. You'll have some free response problems with that, and hopefully that makes sense. And that concludes this edition.